My name is Hajime Tazaki from University of Tokyo. And my talk is more like a lower level implementation stuff about our user space networking implementation, which is called NUSE, the networking stack in user spaces. So the motivations behind this, our small new project on NUSE is from my view, the design of the internet itself is almost done around the 1950s, I don't know. But the implementation is not finished yet of the internet. Implementation of the internet is not finished yet. So if we want to have a new feature of the, for example, in the transport protocols, for example, we may need to have some obstacle before deploying that stuff. So this is kind of the main problem that we are having with the current networking stack, which makes some slow evolution of the operating systems evolutions. And what we want to have, what I personally want to have is kind of the personalization of the networking stack, where everyone can input their own idea onto the networking stack as easy as possible. So let me get into one of the examples that we may face in the current networking stack. So if someone have a new great idea on the new layer 3 or layer 4 protocol, and once we want to try with such a new idea, maybe we will face a problem because their code is not so well tested, and it's also experimental. Then maybe their code will destroy your life because they are implemented in the kernel spaces. Or maybe if you can try with such a new software into the virtual machines, maybe it makes some overhead before using it. So this is kind of the survey report done by the Microsoft researchers, where the question for the survey is when you download and run software, new software, how often do you use the virtual machine in their daily life? And the answer is almost nobody is using in usual life, which means maybe virtual machine is not so enough to use such a use cases. So even though the new feature is merged to the upstream kernel, the usage of this new feature is not so increasing, not so fast increasing. I mean, so this is an observation on and the measurement result in the internet backbone, where some of the TCP extensions, some of the TCP extensions are used in their backbone networking. So, for example, in the middle of the line, it shows the TCP timestamp option is how much TCP timestamp option has been observed in the backbone networks. And this option has been standardized at, I guess, the 1990 something. And Windows 2000 has been introduced with this option. And Windows Vista is defaulted this option by around 2006. So even though we have a default configuration of that new feature, it takes a long time to make a dominant usage of such extension. So, so the current shape of the networking stack takes a long time to deploy it. But in file system world, there is nice work, which is called FUSE, file system in user spaces. And this framework provides kind of the file system personalization without convincing the people who is managing the kernel source code. But people can introduce new file systems without touching the kernel source code. So the approaches that they took for this Fuse implementation is introducing some indirection in the kernel layer and making some interfaces to the user space so that the people can use such useful interfaces to introduce new features. So obviously this indirection makes bad performance compared to the native file system, but they don't care about the performance. But they do really care about the flexibility and the functionality to make it work, make the world changing. So my motivation is why not we have such a feature in the networking stack as Fuse has. So there are already so many alternatives that we already have. So one of them is the container-based one, which provides a really lightweight virtualization, which may alleviate some VM-based deployment approaches. But the containers, the problem from my point of view of the container is that they share the kernel networking stack between the host operating system and the guest one, which may reduce the flexibility of the networking stack. And another interesting approach is that a couple of last 2 or 3 years is introducing the library operating system, which is kind of the user space networking stack. And there are already so many projects like MTCP or Mirage, which is based on the full scratch-based operating system, if I understand correctly. And also porting-based approaches, like also using FreeBSD networking stack, and Sunstorm as well, and the ArcGIS and OpenRoad. There are so many, not only the academic projects, but also the industrial project has been doing creating such a library-based operating system. And also, LAMP kernel is, from my point of view, is kind of the library operating system where the user space program can switch any kind of the networking stack that can be provided by the LAMP kernel. And in the past, there is a kind of Linux-based library operating system, which was called LKL, I guess. But it's almost outdated, and it's not maintained at this moment. My motivation is, the first motivation for this project is introducing the Linux version of the user space networking stack, which is called NUSE. So what is NUSE? So NUSE is the network stack in user space, and it is kind of the library operating system, is the library version of the networking stack of the monolithic kernel. In the current stage, we only focusing on the Linux monolithic kernel, but I believe that any other open source operating system that has a full source tree of the source code of the networking stack can be adapted to this framework by adding some new features. And since each of application have a defined IP address that has on the host operating system, so these frameworks can be considered as a process, kind of the virtualization technique, which is based on the application level, providing the application level virtualization. So comparing to the other existing work, what's the difference with NUSE is we try to focus on our effort to minimize the porting effort of the existing monolithic kernels networking stack. So we are now using most of the mostly latest version of the Linux netnext tree. And this code base is changing very frequently, but we didn't take much time to reflect the latest code to our code bases because our design of the NUSE minimize of the porting efforts. And it's also interesting that the first speaker of this user-space networking stack mentioned, it can provide a full functional networking stack for the recent trend of the high-speed networking I/O stuff like a netmap or IntelliD BDK. And any kind of kernel bypass technology can be combined with such a user-space networking stack. So let me get into more detail about how it works, how NUSE works. So how it works, we need 4 distinct components adding to the existing monolithic kernel. So first one is of course, we need the source code to build the library version of the operating system. And we also need to add some kind of scheduler that kernel space context primitives has been working. And we also provide the Guru code for the application that POSIX API can be used transparently without thinking about whether the underlying networking stack is Userspace or not. And also, since the Userspace networking stuff bypass the kernel network stack, we need to take care of the network I/O, which network card should use with this application. So first one is the kernel modification. So we have been provided the patches to the kernel source tree in order to provide the user space networking library. And we concentrated on adding such a wrapper feature into the architecture, newly introduced architecture, hardware-independent architecture, which is called ArcSym for the historical reason. But by concentrating on by containing all the modification into this hardware-independent architecture, we can easily track the latest version of the upstream kernel code, because we didn't touch any original code in order to use this library version of the networking stack. So second component is the scheduler of the user space networking stuff. So all the stuff of the original networking code is using interrupts, timer, or any kind of context primitive. But in the user space, we can also use such a feature from the user space, but we didn't take such approaches because we can have another context primitive like a facelet or a uContext fiber. So we just re-implement such a scheduler by using right now POSIX thread-based implementation because it's easy to debug. So third one is the POSIX Guru code. We call the POSIX Guru code, which is kind of the hijack function called as ramp kernel defines. So this Guru code provides some kind of the indirection where if the application calls some system call, this library hijack this system call to redirect to our user space code. Besides, instead of the host operating system kernel. So, and the application is not aware of by using such a injection function like a LD preload environmental variable. We can just use existing application as is with such a techniques. And the last one is the network I/O interfaces to connect the NUSE Userspace networking stack to the network interface card. So right now, as LAMP kernel has, we have 4 options to this networking, virtual networking I/O stuff, like a raw socket-based one, NetMap I/O, high-speed I/O, and the IntelliDB as well as TAP-based one. I think we can do any kind of technology. We can use any kind of technology like a PF-Link or, I don't know, pipe or whatever. So how to use it? So we just provide a simple procedure to use the NUSE features. So you can just download the code and compile this modified version of the Linux code as with the specific option. In this case, make library brings you the library version of the Linux kernel stuff. Then execute this library, execute application with the specific option of specified for the NUSE use cases. I will explain about this, how to execute it more detail in later. And since our initial version of NUSE has no fruitful interface for the configuration, we just provided such a simple configuration file to configure the IP addresses or the routing information or whatever. So by using such a user space version of the networking stack, so these two are my ideas that user space stack is useful in the real world cases. The first one is providing the operating system personality, where if you have some new protocol implementation, maybe this kind of framework will be helpful to deploy that stuff. Like right now, multipath TCP, which is kind of a new transport protocol, is having a hard time to upstream their code to the Linux community. But you can use such a library version of the networking stack with such a upstreamed code of the networking stack. And another use case that I have in my mind is kind of providing the process virtualization instances by using the Unix command line. It's kind of VM chaining based on the process-based networking stack, while bridging feature and the connection tracking feature, as well as routing and the web-based web server. This kind of different VM instances can be combined with the pipeline. I don't know how to implement it, but I think this kind of use case is really helpful to make it more funny. So there are, of course, there are still a couple of the limitations in our implementation, like we don't have any fork and exec support interfaces, and we don't have multiple processes supported. And the configuration is also almost static based on the file configuration file. But I think these kind of current limitations can be solved in the future. I don't know. So let me show you how NUSE is working with the live demonstration. So I'm going to present the two different execution results. And one of them is just showing how NUSE is working. And the second part is I conducted a simple performance measurement with the typical application that can be used with NUSE. So right now we have only tested the simple almost 4 programs, 4 applications, and the rest of part is the application that we have failed with the NUSE, the current implementation due to some of the limitation of the current implementations. Okay, so the first example is just executing. Okay. Just executing ping command with the specific destination addresses. So at this moment, we need the root privileges to execute with NUSE, because what we are using for the network I/O is raw socket-based one, netmap, as well as DPDK. All the features requires root privilege, because Linux doesn't have a socking interface as NetBSD has. But so at this moment, we need to use root privileges. And the configuration file is something like this. So each of them are expressing well. Like this line explains how the application uses the underlying networking interfaces, and how the Userspace network library should be configured with the routing information. And one most important thing that when you use the NUSE, we need to have a wrapper shell script that configures such a LD preload magic, as well as some of the library location in the system file. This is also one of the current limitations. So it should work. So as you can see, all the kernel feature of the Linux is printed at the standard console, because all the D message is also redirected to the library, to the application interfaces. And also, application like traffic generator application like iPath is just working with like this. So during this traffic generation, server side has been using the generic version of the networking stack, while client side using the library version of the networking stack. Okay, so let me get back to the original slide. And the second presentation is the simple performance measurement by using the NUSE. So we conducted two different scenarios. One of them was just pinging from the NUSE-based host to some generic networking stack host. And the other one is a layer 3 forwarding scenario where the traffic generator has been located at the outside, then forwarded to the other way around. And the result is shown in this slide. And okay. So almost, I should include the native version of the network, the performance of the native version of networking stack. But so far, we didn't have any time to conduct such experiment. But the result of the left side shows the delay of the measured by the ping command, and the right side shows the throughput achieved by the applications. And we tried the 4 different network I/O interfaces with DPDK, netmap, raw socket, base 1, the tap interfaces. And I don't say any of them are satisfying well of the performance, while the interconnect of these two hosts are the 10 gigabit per second in Ethernet network interface cards. So it's far saturated from the maximum performance, but current status of our implementation is achieving such a performance. And the another scenario like layer 3 forwarding is almost similar result, while almost 10% of the network link is saturated by our NUSE routing scenario. So I don't think it's the best performance of our implementation, but I don't think it's so bad performance at this moment. And I think there is still room to improve our implementation that can saturate such a high-speed network link in the future. And the most important thing that I try to finish with before this conference is try to provide a full functional network stack with the live demonstration. So I think I'm fine at this moment. And let me introduce one more application that I have been also working on. Is the integration of with the network simulator with the Linux network stack of the Userspace versions. So this project is called the Direct Code Execution, which is established by the Mathieu Lacage, who is a crazy French guy, has been working on this project for a long time. And the motivation on this network simulator integration is to provide the reproducible environment of the networking stack code with the controllable execution. And this is the kind of demonstration, visualization where the network simulator has. And each of the circle in this animation has running the Linux network stack. And this kind of movement is provided by the network simulator side, where each of node has Wi-Fi interfaces with the movement. And in this scenario, we are using the mobile IPv6 implementation of Linux, which nobody is using right now. But it can show that Linux stack is running on another application. So what's the difference between NUSE and this direct code execution? Since we are sharing most of the code between these two different projects, almost all the ideas are shared by these project. But one of the key differences between them is since we are using network simulator, and they have a deterministic scheduler which provides virtual clock, kind of. Every execution of the networking stack is deterministic. And for the execution model between them, NUSE is using LD preload to hijack everything, but the DCE is using DLM open-like library code, which provides a single process-based virtualization to establish the multiple instances of the networking stack. And the architecture itself is almost similar. By adding this blue layer, we can obtain such a DCE. And we can also use the debugging of the network stack by using GDB. And also can use burglary as is. And the code coverage measurement is also easily achievable. And finally, also, we have been running the Jenkins continuous integration to detect some of the networking code has been some regression during each of the source code commit. So let's conclude my talk. So I presented an implementation of the network stack in the user spaces, which provide the operating system personalization into the network stack features. And another project is the direct code execution, which provides the flexible network experiment and testing with the deterministic clock. And all the code is available in the GitHub, and I'm always ready to contact with Twitter or email or any other kind of stuff. Thank you so much for listening.